Now let's rotate again and see what it looks like. As you can see, we have a problem. The torus continues to rotate around the origin. What if we want to rotate the torus about its center? Let's jump at the object level again. Create an extract centroid node. Connect the geometry. Select a detail. Here we go, we extract the centroid. Press D on viewport, go to the geometry menu tab, then increase the point size. Now the center point has become much more noticeable. Plug the centroid point to the second input, then dive inside. Now let's create an import point attribute. Connect to it the second geometry, which is a centroid point. Since the second geometry has only one point, the point number will be 0. Okay, now we import the centroid position. I'm going to move the torus to the origin. For that we just need to subtract the center position from the point position. Here we go, the torus is at the center coordinate. Now the rotation is correct. It means we can return the torus to the initial position before rotating it. Now let's add centroid position before the rotation. That's it, the torus jumped to the initial position. Now let's rotate it and see what we get. As you can see, we have a correct rotation regardless of the location of the torus. Let's jump to the object level and reposition the torus, just to make sure our setup always works correctly. That's it, all work as it should. Okay, now let's see the case when we have a lot of geometries and we need to rotate all of them around local centers. First let's copy these two nodes. Then create a copy and transform node. Let's copy the torus 5 times. Then move along the x-axis. Now we can copy them again, along the z-axis. Excellent, we can continue. Let's drop down the attribute VOP. Wire to it the geometry and dive inside. Create a rotate by quaternion. Plug to it the position. Create a Euler to quaternion. Plug to the quaternion input. The output vector goes to the P. Now let's rotate by quaternion and see what we get. As you can see, all toruses rotate around the origin as one solid piece. Now I want to make them all rotate around their centers. To do this, we can use the same method which we did recently. Let's create a connectivity node. Connect to this line. This node creates an attribute with a unique value for each set of connected primitives or points. The default name for the attribute is class. Look, now we have a unique attribute for each torus called class. Later, based on this attribute we can identify each torus inside the attribute VOP. Now let's create centroid points for each torus based on the class attribute. Wire to it the geometry. Since the class attribute is stored in points, we have to specify the point. Select the class attribute from which the centroid points will be generated. Excellent, here they are. Connect the centroid points to the second input. As you can see, the centroid points are inherited the class attribute. Excellent, let's dive inside. Now let's create an import point attribute. Plug to it the op input 2, which represents centroid points. Now we need to set point numbers. We can determine the point numbers by class attribute. Let's create a bind node and bring in the class attribute. The attribute type is an integer. Type a class. OK, now let's connect the class to the point number. Excellent, we imported the centroid point positions. Now we need to subtract the centroid positions from the torus's positions in order to simply move the toruses to the origin. That's it, they all jump to the origin. After rotation we can already return them back by adding the centroid positions. Here we go, they return to their original places. We can press Alt, then click on the wire just to add a dot, then reshape. Now we can rotate by quaternion and see what we get. Great, they all rotate around their centroids. OK, now I want to randomize the rotation of each torus. For that let's create a random node. I want to generate the random vectors based on the class attribute. From this menu select the 3D vector output. Now let's create a turbulent noise. Plug to it the random vectors. Select the original Perlin noise. The output should be a 3D vector. Excellent, now let's increase the noise amplitude. Then plug the noise to the rotation vector. That's it, we got random orientation for each torus. You can control the rotation amount by noise amplitude. Now I propose to stop this setup and start doing something new, during which we will learn a lot of cool things related to quaternions. OK, let's get started. This time we are going to use this simple box that I prepared in advance. Now let's create a line. Put a 50 for points. Change the direction along X. Put a 15 for length. Excellent, let's create a copy to points node, then copy the box onto the points of the line. Let's drop down the attribute VOP. Wire to this line. Then dive inside. Now I want to introduce you to the new node related to quaternions, that is called spherical linear interpolation. This operator computes a spherical linear interpolation between its two quaternion inputs and outputs the intermediate quaternion. This interpolation will always be along the shortest arc. Let's leave it temporarily, we will need it soon. Drop down the bind export node and create an orient attribute. The attribute type must be vector 4. Let's also create a quaternion node. Then connect to the bind export. Now I want to gradually rotate the boxes around the x-axis. For that, let's create a gradient from 0 to 1 along the line. To get this gradient we can divide the number of points by the total number of points. The num-pt is a total number of points in the geometry. Look, the output of the divide node is integer because the first input is also integer. Since we are going to create the gradient from 0 to 1, this should be a float. Let's convert the first input from integer to float just to have float output. This operator converts an integer value to a float value. That's it, now let's export this attribute and see what we get. I call it curve mask. Let's open up the geometry spreadsheet and check this attribute. Look, we have a gradient from 0 to 0.98. The maximum value will be 1 if we subtract 1 from the total number of points because the point numbers start from 0. Okay, let's create a subtract constant. By default this node subtracts 1, which is what we need. Let's check the curve mask attribute. Here we go, the mask range has become from 0 to 1. Okay, let's go ahead. Now let's delete the bind export node, then plug this to the angle. To expand or narrow this range, we can create a multiplier. Here we go, we can rotate gradually as we like. Now I want to give them nice colors. Let's create a hue shift node. Connect the output color to the CD. The default color will be red. We are going to shift the red color by this range. Let's tweak the shift amplitude. That's it, we got nice color gradients along the line. We can arrange the nodes a bit to make the setup more readable. Now it's time to use the spherical linear interpolation node that I temporarily left. First, let's create a quaternion invert node. Invert the rotation. Take a look, we got exactly the opposite. Let's get the original rotation back. Now I'm going to interpolate with inverted. Connect both quaternions to it. The output quaternion goes to the bind export. Let's tweak the bias. Here we go, we can blend two quaternions. Now I propose to blend them in an interesting way. Create a ramp parameter. Select the spline ramp. Connect to it this range. The ramp output goes to the bias. Now let's edit the spline ramp. Okay, something like this, mixing occurs only in the middle. Now I propose to shift the input ramp range and see what we get. Let's create an add node. Promote the second input. Let's give it a name. Put -1 as the minimum limit. Now let's tweak this parameter. Here we go, by moving this parameter we shift the region where the blending occurs between the two quaternions. Okay, let's continue. Now I want to edit the color based on the distance between the two quaternions. For that we need a quaternion distance. We are going to measure the distance between the initial quaternion and the blended quaternion. Excellent, now we can use the distance as a color multiplier. Create a multiply node. Before multiplying, let's fit the distance. Put a 1 for destination min and 10 for destination max. Now let's multiply the color by the distance. Excellent, let's check how it looks in action. So, in a region where the mixing occurs, the color intensity increases 10 times. Great, the last thing I want to do is change the p-scale where the blending occurs. Now let's create a p-scale attribute. We need one more fit range node. Connect to it the distance. Put a 1 for destination min and 1.5 for destination max. Then connect it to the p-scale. Let's do a final look. That's it, the p-scale also changes where the mixing happens. Well, let's stop at this. We are practically studying all the main nodes associated with quaternions. In the next lesson, we will study matrices that give us an alternative way of doing similar things and more.